All right, 7.2, we're going to continue our discussion of decimals. We're going to start looking at operations on decimals today. So operations mean addition, subtraction, multiplication, division. So we're going to start with addition and subtraction. So in addition and subtraction with decimals, we want to line the decimal points themselves up, and then we will add and subtract the same way we did with whole numbers. So we're going to do it for this particular example, but then I want to talk about why it works, because it goes back to things we've already talked about as far as justifying why this process should make sense. So I have 4 and 33 hundredths plus 3 and 26 hundredths. So this says I'm supposed to line the decimal points up, which I have, and then I add and sort of ignore the decimal points in the middle of the addition. There's lots of strategies for adding. The one that's most familiar to all of us is to start on the right-hand side and to add from the right to the left, which is sort of backwards of how we read. I would get a 9 here, 3 plus 2 is 5, and then 4 plus 3 is 7, and then I bring the decimal point directly down. So I have 7 and 59 hundredths. But I'd like to show you why this actually makes sense from the standpoint of place value. So I've got the number 4. And then the 3 in the first location is in the tenths, so it's 3 tenths. And then I've got a 3 in the hundredths location, so I have 3 100ths. So this would be like the expanded form way of writing this decimal out. And I can do the same thing with the number 3 and 26 hundredths. So I have a 3, and then I have 2 tenths, and I have 6 hundredths. If you really wanted to do them like as 26 over 100, you could do that too, but this one breaks it down a little bit more than to do it that way. And then what we talked about when we did fractions is we can add the whole number pieces. This is one of our approaches. That would be 7. These two have the same denominator, so 3 tenths and 2 tenths is 5 tenths. And then this one and this one have the same denominator, hundredths, so 3 100ths and 6 100ths would be 9 100ths. And I can write that back into decimal form as 7 and 59 hundredths. So this idea of lining up my decimal points is really all about place value. So we're going to do an example of one where we actually have some context. Some of your problems have context, as you know, and some don't. When they do have context, if there's any units or things, we want to make sure we include them in our answer. So a stock's price dropped from $63.28 per share to $27.45 per share. What was the loss on a single share of this stock? So what operation am I being led to use on this problem? It's subtraction, right? The product's going down in price, and we want to figure it out, the difference. So I have 63 and 28 hundredths, and I'm going to subtract the 27 and 45 hundredths. So we're going to utilize the same things that we would do if it were whole numbers, now that we've lined up the decimals. So on the far right, in the hundredths place, I have 8 minus 5, so I get 3. However, in the tenths place, I can't really do 2 minus 4, so what do? I borrow or I regroup. So regroup is one of those phrases that we hear a lot in curriculum these days. If you haven't heard it yet, you will. And so we want to take the 3 and we want to make it a 2, and we regroup that 1 over here. And if you really think about it, what you're doing is you're taking a dollar bill, because this is about money. You're taking a dollar bill and you're turning it into 10 dimes. So when I take those 10 dimes and add it to the 2 dimes, I now have 12 dimes. That's really what's happening. So I have 12 dimes now minus my 4 dimes. I take away 4 dimes and I have 8 dimes left, right? And the next place value over, though, I can't do again the 2 minus the 7. So again, I have to regroup. So I regroup by taking the 6, and I'll make it a 5. So this is like taking a $10 bill, right? And breaking it down into ones. So I now have 10 ones plus my 2 ones, so now I have 12 ones. If I have 12 ones and I take away 7 ones, I'm left with 5 ones. And then 5 minus 2 for my tens place gives me 3. And I have units of dollar signs, so I'll use them. This would be $35.83. Kind of like to pinpoint just so that you're aware, decimals don't really occur until the end of elementary, sometimes the beginning of secondary, like the beginning of middle school or junior high, depending on what the school district does. So you're usually looking at either a 7th grade math class or maybe a pre-algebra class before students are actually using decimals. And you might think, well, it's not that much different than whole numbers, and it's not that much different, but it still usually comes after fractions, and just like what we've done in our class here. Okay, so we're going to look now at multiplication. So addition and subtraction feel just like what we do when we do whole numbers. There's really very little difference to them except for the lining up the decimal point, and then after that everything works out the same. Multiplication has some nuances that actually feel a little bit different, more different than that. So with multiplication, we multiply the way we do with the whole numbers, but we don't line up decimal places and bring them down like we do with addition and subtraction. What we do is we count the number of places after the numbers we multiplied on the decimal points. We add those values all together, and then that's how many decimal points will be in our product. And it sounds so much more confusing than what we really physically are doing when we do it, but there's just no real concise way to write down what we're doing. So for example, when I have 0.3 times 0.7, I multiply just like it says 3 times 7. And what's 3 times 7? 21. And then I count the number of place values after the decimal. So here's 1, and here's 1, so that makes 2. There are 2 decimal points. So my answer, where I got the 21, has to have 2 decimal points as well. So counting over, the decimal point would have to go here so that there's 2 values after the decimal point. That feels a little funny. Why would that work? That's a little more mysterious than just dropping down the decimal point that it happened with addition and subtraction. So let me show you again why it works. And we're going back to fractions. I know they're not maybe your favorite, but they work really well for justifying these. So 3/10 as a decimal looks like 3/10 as a fraction. And 7/10 as a decimal is 7/10 as a fraction. And if I multiply across the top, there shows up that 21. But what do I get when I multiply across the bottom? 100. And what do I do to put 21 over 100 in decimal form? Well, I need to be landing in the hundredths place. So the hundredths place is 2 decimal points, 2 places after the decimal point, and there's my 21. So it does go back to place value, but the justification is just a little bit different. And it has to do, again, with multiplying instead of with lining the decimal points up. Let's look at division. Division also has kind of a nuance to it that makes it a little bit different. So when we're working with division, we want to make the divisor, right? The divisor is the number you're dividing by, a whole number, by moving the decimal point in the divisor and the dividend, that is what you're dividing, an equal number of times. And then once again, we divide as we do with whole numbers. So let me show you that in play. We have 0.75 divided by 0.5. I'm going to do what they said, right? So I have 0.75, and it's being divided by 0.5, like so. And what they said in the description is that I need to make the number on the outside of the division symbol a whole number, and I do that by moving 1 decimal place over. And so I do one here as well. So I'll rewrite what it changes to just for clarity's sake. Now I will be dividing 7.5 by 5. And that's what it really says. Okay? And then I just do it, piece by piece. So 5 goes into 7 one time. 1 times 5 is 5, and I subtract. This gives me a 2. I can ignore the decimals right now with the division pieces of it. Oops, 5 goes into 25 5 times. 5 times 5 is 25, so I'm done because I've got a remainder of 0. And then the decimal point itself just comes straight up, again lining it up kind of like what we did with addition and subtraction, and I have the answer 1.5. But again, like, why should that work? Well, it works again from a fractional standpoint. So I'm doing 0.75 divided by 0.5. And when I move decimal points over, because that's what I'm told to do here, is just shift it. You know, if I shift it for one, I shift it for the other one, the same number of values, and I'm allowed to do that. But if you think about it from the standpoint of fractions, shifting a decimal really just means that you're shifting the place value. If I shift it once, I'm multiplying by 10. If I shift it twice, I'm multiplying by 100. 3 times, I'm multiplying by 1,000. So I'm allowed to do this with fractions. If I multiply the top by 10 and multiply and the bottom by 10, I've not changed the overall fractions value. And if I take 0.75 times 10, I get the 7.5. And if I take 0.5 times 10, I get the 5. And so you see this piece coming out of that perspective that allows me to move into this into the same values. Okay, so it's again coming from place values within fractions. Hang on just a second. Okay, we're going to do scientific notation next. So scientific notation shows up in this section primarily because the basic form of a numeral in scientific notation often has decimals. So the basic form is a times 10 to the n. The number a is between 1 and 10. It can equal 1, but it has to be less than 10, so it's always a single number in front of the decimal point. It can have decimal value, though. It doesn't have to be whole numbers. So it's not telling you that a is an integer or something like that. A is any number between 1 and 10. It does tell you that the exponent n is an integer. So the exponent itself needs to be positive or negative or 0, but it's a whole value, not a decimal value or a fractional value for an exponent. I teach scientific notation a little bit different than your book might. Or many books might, and there's a very good reason for it. So as I'm showing you how I think about it and do it, you'll see why that I'm doing it that way. One of the most difficult things about scientific notation has to do with changing them into and out of scientific and or standard form. So when we are moving from standard numeral form into scientific form, we want to move our decimal point to create a value that is between 1 and 10. We want our number to be between 1 and 10. We count the number of moves that we made. Our exponent is the number of moves. If our value is large, as in that it's larger than 10, then the exponent's positive. And if our value is small, that is, it's a value that's less than 1, then our exponent is negative. So a lot of times what you hear when we get to scientific notation is if the exponent's negative or positive, you move it right or you move it left. The problem with that is that it matters whether you're going from scientific to standard or standard to scientific as to which direction you move the decimal based on the positive or negativeness of it. And it can be confusing because you have to be very careful about which direction you're moving. If I think about it from this perspective, where I have positive exponents and they mean large numbers, and negative exponents that mean small numbers, I don't have to be extra careful about which direction I'm going, scientific to standard or standard to scientific. So let me show you how it works with an example. We have the number 298,000. Okay? And I want to take this 298,000, and I want to put a decimal point somewhere in the number so that the number is between 1 and 10. Where would the decimal point go in the middle of all these numbers? Yeah, between the 2 and the 9. The number 2.98 is the only place I can put the decimal so that the number will be between 1 and 10. Is that part okay? Good. Now what we want to do is, now the original decimal actually started out at the end because we don't see it. What I want to do is I want to figure out how many places I moved, right, how many times I moved to get the decimal over here. How many did I move? Well, I moved it, 1, 2, 3, 4. I moved it 5 times. Are we good so far? So this will be times 10 to either the 5 or the negative 5. So we look at the number and we say 298,000. Is it a big number or a small number? It's a big number. And again, my definition of big means bigger than 10. Definitely bigger than 10. So a big number means I have a positive 5 exponent. That's it. I don't have to decide, did I move it from left or to right? It doesn't matter. The number was a big number, so it's a positive exponent. Okay? We can do the same thing with a small number. And if the number had been small, it needs to be smaller than, so I'll just do sort of a little bitty example over here. If the number were smaller than 1, it's a small number. That would be this example. So in this example, which is 45 10,000ths, where would I put a decimal to make the number between 1 and 10? In between the 4 and the 5. And I will count the number of places I moved the decimal. What is it? 3. So it's times 10 to the 3. But is it positive 3 or negative 3? Negative, because the number is a small number. Does that make sense? Okay. We can do the same thing by doing the other direction. We can start with something in scientific notation, right? Like if we sort of did this problem backwards and we started with 2.98 times 10 to the 5th. And we can turn it into standard form. Again, a positive exponent means my number will be large. And a negative exponent means my number will be small. So I don't have to do so much worrying about do I move it right or do I move it left. That comes about automatically when you look at it and you say, oh, what do I have to do to make it a big number? Oh, I have to do this, right? How do I make it big? How do I make it small? So here's our example. We have 3.2 times 10 to the negative 5th. Well, the 5 tells me I moved the decimal 5 places. The negative tells me what? That the number needs to be small. I need a small number. So in order to get a small number, is my decimal going to move right or is my decimal going to move left? It's got to move left in order to get the number to be smaller. So it starts out with 3.2, and I'm going to need to move it left, so I need some 0 placeholders over here. Just put several in. And you count 1, 2, 3, 4, 5. Oh, I put in just enough. So my answer is a point, and you can put a 0 in front if you wish. I have 4 zeros, and then 3, 2. And I could use the same example if you wish and make it times 10 to the positive 5. And if it's positive 5, it tells you, right, that it needs to be big. And the way that I get it to be big is I move the decimal to the right 5 times. So 1, 2, 3, 4, 5. I'd have a 3 and a 2, and then I have 4 zeros, which would be the number 320,000. So positive exponent makes a big number, or it came from a big number. A negative exponent means it makes or it came from a small number. Scientific notation, we don't just use this for everything. What kinds of things use scientific notation? Because there's uses for it that are practical, and there's uses for it that are not. Where is scientific notation practically speaking used? And don't tell me just science, that's not what I mean.
Is it used on calculators whenever it maxes out?
The calculator will use it when it maxes out. If you get too big or too small of a number, it'll put a capital E in something, and it means times 10 to a power. It will use on calculators, yep. So in particular, it has to do with numbers being big or small. So can you think of a place where a big number uses scientific notation? I mean, it is in science, but like what specifically? What's something that's big that uses scientific notation?
Aren't there like some forms of like scientific measurement that are too big, so they use that? Or like
Yeah.
too small?
Can you think of something that we measure in science that's really big?
The sun.
The sun. What about the sun? Maybe the distance to the sun.
Right.
Or the size of the sun, right? Yeah, so think solar system, big scale kind of things. Scientific notation, definitely. Can you think of something small in science that you use scientific notation for? Has anybody taken chemistry at all? Any chemistry in high school? Seriously? No chemistry in high school for any of you?
Not that I remember.
I don't even want to know where y'all went to high school.
My high school doesn't
Don't even
have
know.
chemistry.
Wow. I can't even imagine a high school without a chemistry. Okay. How about if you guys ever been seeing a periodic table?
Oh yeah.
Okay, good. That's good.
I mean, I'm
Restore my faith a little bit.
I took chemistry.
You took yours has been a long time ago. I think that's fair. You took chemistry. So in chemistry specifically, but physical science would have been another place you probably would have seen it. You talk about the size of like atoms, the size of neutron, like the electrons and the neutrons and the protons, things like that. They're measured very, very small, right? You need scientific notation to work with those well because the numbers are so very small. So in particular, scientific notation is for things that are extremely large, think distance to the sun, or extremely small, think the size of an atom, okay? That's what you're looking for when you're thinking about scientific notation. All right, and the reason we want to change them is because working in scientific notation is far easier than working in standard form when the numbers are very big or very small. So if you take a look at this example, are these numbers very big or very small?
very big.
They're very big. And while you very well may be able to turn them into the very big numbers and do the multiplication, that's going to be a lot of work. Okay? And undoubtedly, most of us will make some kind of mistake because there's going to be a lot of zeros. And keeping track of a lot of zeros usually ends up with the mistake being made. It's just the way it is. There's a much easier way to do this, and it has to do with the things we've already learned back in chapter 6. So, first of all, let's look at the 8 times 6. What is 8 times 6? 48. So I'm allowed to shift these numbers all around. That's called the commutative property. We've talked about that. We can change the order of all the multiplication because it's all multiplication. So I can multiply this to be 48. And then these two numbers right here are in exponential form. And we've talked about properties of exponents. That happened in 6.3. So what do I do in order to combine these 10 to the 12th and 10 to the 15th? I add. If they were divided, I would subtract. Okay? So these are multiplied, so I'm going to add the exponents. What is 12 plus 15? 27. Now, I'm not done though, because the direction says to write the result in scientific notation. And why is 48 times 10 to the 27th not scientific notation?
Because it has to be between 1 and 10.
It what?
The 48.
The 48. This number 48 is not between 1 and 10. Right? It's bigger. So I don't get a stop right here. If this had started, if this number had said, like 4.8 right here, we would be done and be fine. But it simply doesn't. It says 48. So I do want to change it into 4.8, but I can't just change 48 into 4.8 and call it good, right? Something else has to change. There's got to be some compensation. So when I take the number, I don't think I should have used a dot here because I'm about to use a dot with the 4.8, so I'll use an X. When I take the number 48 and turn it into 4.8, was 48 a big number or was it a small number? It's big because it's bigger than 10, right? So in order to compensate for the fact that I just made it smaller, I need to make the exponent bigger as well. So my 27 will become 28. Why? Well, because I made the exponent, I had a big number, so I'm going to compensate by making my exponent bigger. And if I had had a point where, and again, I'll just throw in an extra little example over here, where the answer ends up being something like this. I'll change the number so that it's not confusing when you're looking later. 0.32 times 10 to the 12th. Let's say this is our answer at the end. I've done some multiplication or division, and this is the answer I end up with. Well, it's still not scientific notation because 0.32 is smaller now than 1, right? So I have to also change it to be 3.2. But what will I do to the exponent to compensate? Subtract 1. Yeah, I make the exponent 1 smaller to compensate, so it becomes 10 to the 11th. Okay, so we can shift the exponent based on how many shifts that we're making to our number itself. But this is so much easier, because otherwise what you would have to do, and this is what I've had students do on a problem like this when they forget on a test before, is they turn all that into times 10 to the 12th. They write out these long numbers with zeros, and they write out another long number with a 0. They always make a mistake. I don't think I've ever had anybody do it and not make a mistake when they've tried to turn this into standard form and then do the problem and then go back into scientific. There's just too many places along the way to make an error, okay? So this is very convenient to be done within scientific notation itself. Laura?
When dealing with like negatives, I don't know if the book has been very sneaky about throwing in negatives. So for like negative 48 times 10 to the 27, is it still the same thing?
Okay, so when we're working with scientific notation, take a look back over here real quick and notice, oops, where am I needing to go? One more time, I think. Notice that the number can't be negative and be in scientific notation. And that should kind of make sense anyway, because we're talking about things that are measured in like measurements, and measurements aren't negative.
Mm-hmm.
So for scientific notation, you won't see any negatives happening at the beginnings of these numbers.
Okay.
Yeah. Any other questions?
The exponents can be negative.
The exponents can be negative, yes, because they simply mean something small. Yes, so your exponent can be negative, but the number in the front, like our 48, wouldn't be. Anything else? Okay, this is where we're going to stop for today because it's a reasonable place for us to stop. All right, so we're done just a little early.